Let's see how to solve ordinary linear differential equations using Laplace transformations. Okay, so let's say we have a differential equation a naught y double prime of t plus a1 y prime of t plus a2 y of t is equal to q. Now here q is a function of t. Remember, this is double prime, so yes. And what we have to do is we have to find y is equal to f of t, right? So we have to find y, and here a naught, a1 and a2 are constants, and the conditions, let's say, that is given, conditions given are y of 0 is equal to 0 and y prime of 0 is equal to not 0, let's say c1, it could be anything, c2. Okay, let's see how we can go about solving this. Let's start with the statement itself. A naught y double prime of t plus a1 y prime of t plus a2 y of t is equal to q. Now what we'll do is we'll take the Laplace transform of both the sides. So Laplace of a naught y double prime of t plus, and what we can do is, remember, Laplace we can split it up for all of them separately. So Laplace of a1 y prime of t plus Laplace of a2 y of t is equal to Laplace of q. Now here constants we can take it out, so this becomes a naught Laplace of y double prime of t plus a1 Laplace of y prime of t plus a2 Laplace of y of t is equal to Laplace of q. Okay, now that we have done this, let's evaluate. Now a naught, now remember the theorems we saw, so this is going to be s square capital Y of s minus s y of naught minus y prime of naught. This is as based on the theorem, plus this was this. Now let's take up this. So this will be a1 times s capital Y of s minus y of 0, again based on the theorem. Then this one, so this would be a2 times y of s equal to Laplace of q. Now let's take together common terms. So y of s, capital Y of s, capital Y of s, capital Y of s. So this would be a naught s square. This looks like, okay, s, a s square plus a1s plus a2, and common here is capital Y of s, yes, minus, so minus a naught s y of 0, s y of 0 minus a naught y prime of 0 minus a1 y of naught equal to Laplace of q. Okay, now let's keep it as it is, s square a1s plus a2 capital Y of s minus a naught s. Now remember, a naught, a y of 0 is equal to c1. So y of 0 is equal to c1. So I can put it here. C1 A naught S minus, now y prime of 0 is C2, so minus A naught, and I can take C2 here, minus A1 again C1 is equal to Laplace of, now let's rearrange the terms. Okay, let's say A naught S square plus A1 S plus A2 capital Y of S is equal to Laplace of Q plus, this all will become plus, right? So A naught C1S plus A naught C2 plus A1 C1. And now what we can do is take this to the denominator on the other side. So what? Capital Y of S is equal to Laplace of Q plus A naught C1S plus A naught C2 plus A1 C1 divided by A naught S square plus A1S plus A2. We have got this, and which means what? Let us say this is equal to capital F of S, this entire term. So to simplify it, we have y, capital Y of S is equal to capital F of S, right? So if we, now we need the function, so we take the Laplace inverse of Y of S, which means Laplace inverse of F of S. So indirectly what I'm saying is we are going to take the Laplace inverse of this after simplification. Okay, so which means what? This is nothing but Y, and this would be nothing but F of t. And this is what we had to arrive at. Now let's do one problem to see how this works. So let's say the differential equation given to us is y prime minus 5y is equal to e to the power of 5x. And the condition that is given is y of 0 is equal to 2. Okay, so now what do we do? Take the Laplace transform of both the sides. So y prime minus 5y is equal to Laplace of e to the power of 5x. Okay, now this we can split it up. Laplace of y prime minus 5 times Laplace of y is equal to Laplace of e to the power of 5x. Okay, now Laplace of y prime is, let's say, s times uh, f of s minus y of 0 minus 5 times Laplace of y, that would be f of s is equal to, now this we know from the table, this would be s minus 5. Now let's do the substitutions. So s of f of s minus y of 0 is 2 minus 5 f of s is equal to 1 by s minus 5. Okay, f of s is common, so this becomes s minus 5 of f of s equal to 1 by s minus 5 plus 2. Now this becomes 2s minus 10 plus 1 minus 9. So 2s minus 9 by s minus 5. Now if we bring this s minus 5 to the other side, this becomes square. Now we arrive at something that you need to be very good at, and that is partial fractions, right? We have to split it into partial fractions. Let me do this separately. So we have 2s minus 9 by s minus 5 square is equal to a by s minus 5 plus b by s minus 5 square. By the way, I have a separate playlist on just partial fractions. Okay, now let's add them up. So 2s minus 9, this would be a times s minus 5 plus b times 1, because s minus 5 is already there here. So this would be equal to as minus a5 plus b is equal to 2s minus 9. Equating the terms, we get as is equal to 2s. So as is equal to 2s, so which means a equal to 2. Similarly, uh, we have minus 9 is equal to minus a5 plus b. Now a is 2, so this becomes minus 10 plus b minus 9. So b is equal to 1. So that means our partial fractions would be what? If we split this into two fractions, sum of fractions, we will get a is 2 by s minus 5 and b is 1. So plus 1 by s minus 5 square. Okay, this is f of s. Now we want the function, so we take the Laplace inverse of f of s, which means we take the Laplace inverse of 1 by s minus 5 plus Laplace inverse of 1 by s minus 5 square. This is 2 times Laplace inverse of this is e to the power of minus 5x plus, no, we are talking in terms of say t. We are not talking in terms of functions of function of x or function of t. Okay, we have taken it as x, so this will be x. So you need to be careful. E to the power of 5x plus, and this is going to be x e to the power of 5x. So this is the function y is equal to. So that is applying Laplace transformations to solving ordinary linear differential equations. That's it. Bye.